And well, our first speaker will be Clément Gazzino from CNES for the last presentation about biases. And the title is GNSS Satellite Hardware Biases Stability Over Time, Long-Term Analysis of the Products from Several ACs and Impact from Flex Power.
Yeah, it works. Okay, thank you. I'm Clément Gazzino. I'm working at CNES in a navigation team as well as the orbit determination team. And we'll talk about the long-time stability of GNSS biases and the impact of flex power. So, as you may already know, there are some errors coming from GNSS hardware stuff, like instrumental biases coming from imperfection on, or physical limitation on electronic of satellite and receiver, as well as hypothesis of synchronization in signal reception. That is not always true. And those biases that link to the hardware can be assumed to be stable over time because it's linked to material, not to a software. And we'll see that it's not always the case, and according to what is provided by some analysis center. So I will here focus on GPS hardware biases on L1 and L2 bands, namely between the civil and the military signal. So if I look on some biases given by some analysis centers at the IGS, like GRG, V1 or IGS combined, either in final, rapid, or RTS, we show something of like I presented on the figures, with one color per satellite. So you see first on the right-hand side, we have some relative stable behaviors, although on some days you have some steps, something that is happening. And on the left-hand side, you have something more oscillating or more fluctuating over time. So something may happen or may be hidden behind this phenomena that seems to represent the same physical stuff. So we can do things as we want. So we can take one satellite and look what happened for each analysis center. So I took all the analysis centers I could find, either rapid, final, ultra rapid, or real time. And we see that we have a lot of families that may emerge from this analysis. Some curve like code or GRG products that behave the same. We have some case or technical of science or VM rapid that are the same. We have the CNES real-time that is oscillating in the middle. So something may be behind this, and try to look closer what happened. So I decided to reconstruct all those DCB products by taking measurement from a ground station. So I took here the STGO station from St. John's in Canada, and building the code difference between the code GPS 1C, civil modulation, minus military modulation, the 1W. And we can assume that the biases are expressed as a term depending on the satellite, minus a term depending on the station. And you see on the graph on the left-hand side that you have some satellites that are very stable, a bit oscillating with noise, and the steps that we saw just before that's still appearing here, either on the C1 CC1W signal on one hand, and on the C2L C2W signal on the other hand. So what I wrote here, two types of behaviors: some constant satellites and some satellites with jumps. So now we can look a bit closer. On the previous curve, I draw 1 point per day as a mean of the values. Here we will look a bit closer at what happened inside a pass. So I look closer on a few days from STJO and TLG station with a bias C1C minus C1W. And you see something strange. For instance, in STJO, you have 2 passes per day, 2 passes per day, and 2 have different values. Values is constant on each pass, but different. And if you look at the day number 5 on the curve, on the orange and blue curve, you have something that is not constant anymore. You have something that is jumping. So it's constant before the jump, constant after the jump, but not, of course, during the jump. So how to assess that? So I try to compute not a mean per day, but a mean per pass. And you see the second figure at the center but you see a mean. So in the blue curve in STGO, you have for a given day 2 points because the two passes have different values. Passes are constant. You can see it on the graph on the right-hand side because I draw the standard deviation of the pass. And it's rather a low value, except from the pass on the day number 5, where something happened. There was a jump inside this pass, and the standard deviation is increased. So this is a well-known phenomenon linked with flex power. So like what happened yesterday, but within satellites, we have an increase of the signal-to-noise ratio on the military signals. And we can see this effect on GPS satellites as well as on Beidou satellites. So for GPS satellites, this occurs in the C1, CC1W on one hand and C2, C2W on the other hand for block 2RM and 2F. It's also seen on Beidou, but I won't go deeper into Beidou satellite for this presentation. There is a number of studies that analyzes the flex power, and particular flex power detection based on carrier-to-noise ratio on one hand. And I found other studies back to 2019 studying the impact on DCB. Sometimes assuming that we know the localization of the flex power activation on the Earth to detect it, or to use a smoothing technique and so on. So I want to detect the flex power activation on and off without assuming that I know where this flex power occurs, but taking another hypothesis. So first, I will take 10 stations on the Earth, all equipped with septentrial receivers. So I draw the map here from the station I chose, and the visibility circles from the GNSS orbits. And I will try to find a way to determine constant biases, but not over a day, but over a flex power on and a flex power off regimes. So I begin with a simple step. So I told you before that flex power occurs on satellites with block 2RM and 2F, but not on block 3. So I will take a long time interval with block 3 satellites, building an observability matrix with all the -1 and +1. So just here is written so that you see how I computed, but this is something rather unknown. And zero mean constraints on my satellites, with my GPS-3 satellites on one hand and my 10 stations on the other hand, and I solved the problem. Nothing new here. And then what I found is something is written on the table in the right-hand side. That all the biases from the station I chose are almost all the same, except the one in the Pacific Ocean that is a bit smaller. But we see that for all septentrial receivers, we have almost all constant values, either in C1, CC1W and C2, C2W. And on the other hand, on the table at the center, you see that almost all GPS-3 satellite biases are constant on the L1 band, not that constant on the L2 band, but I suspect because this difference is a bit noisier than the first one, and can apply some weighting to address it. But either in L1 band, something is almost constant. So choosing the GPS-3 satellites as reference satellites for our flex power effect can be a good thing. Then I remove the station bias, and I here an example on the G32 satellite, and you see directly the when flex power began. So it's around April 1st last year. So before April 1st, all the observations aligned very well on a given value. Here is minus 0.5, I think. And after that, you have some stations that see higher values, some stations that see the jumps, and some stations that see the flex power on regime. Then I will use this effect to detect when the flex power starts and ends. So my second step is to draw an algorithm to detect when flex power occurs. So the curve is a bit cumbersome, but I will explain it. So I'll draw all the steps of my algorithm. So first, I remove the station biases, as I explained. Then I compute the means of all the visible stations. So I have one curve, the purple curve that is on the screen, either on C1C, L1 band and L2 band. Then I applied a low-pass filter. You see that on the L2 bands, the difference is very, very noisy, and I have to apply a filter. So here is a forward-backward first-order Butterworth filter. I applied it, and you see the light blue curve, where you realize you see this constant values on small intervals. Then to detect when flex power occurs, I made a correlation with a step function. And you see the yellow curve, that is the result of the correlation with the blue curve. And to detect when flex power occurs, I have to have a threshold. This is the green curve. So when the green curve is appears, is when there is a step is active, and then with the black dot, I detect when the flex power occurs. So on the C1, C1W is easy to see. On the C2, C2W is a bit more difficult. That's why we have to smooth the value. And then on the third step, we can consolidate the estimated values with histograms. So I take all my interval, all the smooth value, and I try to fit two Gaussians on the drawn histograms. So it's like a nonlinear least square solution to compute. And by retrieving the mean of the two Gaussians, you basically have the two bias values in flex power on regime and flex power off regime. So here's results. So not for the figure, but you see how it looks like. For some satellites, nothing is detected. So question is, those satellites have flex power, or just my algorithm wasn't able to detect them because the jumps were too small. Particularly for the L2 bound, I suspect the jump were very small because it's noisy data, and perhaps the low pass filter was not well tuned. But if nothing is shown here, perhaps it was have no effect on the positioning. And we can do a comparison with GRG products. So here is a computation between the value I found it with my algorithm and the value that is provided by the GRG Analysis Center. You see that before April 1st, all values are in agreement and aligned to given small value. And after April 1st, the value are spread around a mean value, meaning that if you compute one value per day, you end up at the mean between the high pass and low pass, high value and low value of the biases. Whereas if you compute one value per pass, you have something more realistic. What effect does it have on the Melbourne-Vibena combinations? So I computed the 1W, 2W Melbourne-Vibena and 1C2L Melbourne-Vibena combinations. And I computed the difference between the two, the civil and the military Melbourne-Vibenas. In one hand, correcting with flex power bias, it's a range curve, and the other hand, without correcting with flex power bias. And you see that at April 1st, around 1 a.m., you have a jump of 0.1 wide lane cycles. You see that you can see the difference between the military Melbourne-Vibena and the civil Melbourne-Vibena if you don't correct with the flex power bias. Question now, which signal is jumping? So on the signal to noise ratio, we saw that we have an increase of the SNR with the military signal on the military signal on the 1W and 2W. But if you draw the Melbourne-Vibena combinations, in fact, the military Melbourne-Vibena combination is constant, and the civil one is jumping. Something strange is happening here. So the military SNR is increasing, but the civil Melbourne-Vibena is jumping when there is a flex power. So a bit of conclusion. So for a GPS measurement treatment, we know that we have to use intermodulation biases. For instance, for Sentinel-6 missions, we have receiver with civil bias, but we use a military constellation bias to correct the signal, so we have to use intermodulation bias. And also for integer ambiguity resolution, you always need to have an alignment between the signal modulation and your correction modulation. So analysis center computes those bias, but given one value per day. And what I wanted to demonstrate is one value per day is not enough. We should use the capability of CNX files to give values that are with a rate that is higher than one per day, but perhaps twice per day, or basically, if you can compute and detect when flex power is active, to give one value per flex power on or flex power off interval. So as evolutions, we could do the same with Beidou. And all what is done here has been done in different time, and we can expand the method for doing in real time. For instance, using not forward-backward filter, but forward filter, assuming that GPS results have a constant biases. And here are the references I use. Thank you very much.